The separation of alkane isomers is of great importance in the petroleum industry. If we look at the isomers of C5, C6, and C7 alkanes, we note that for C5 alkanes there are three isomers: normal pentane, 2-methylbutane, 2,2-dimethylpropane, or otherwise called neopentane. The boiling points are shown here, and we see that there is a difference of about 20 degrees in the boiling points. But if you look at the research octane numbers, we note that the branched isomers have significantly higher research octane number than normal pentane. The same is true for the isomers of hexane and heptane. The branched isomers have higher octane numbers than the linear ones. And if we examine more closely, we note that the di-branched isomers have higher octane numbers than the monobranched isomers. This is true for the isomers of hexane and also for heptane. The di-branched isomers are preferred components for incorporation into the gasoline pool. Therefore, there is an industrial need to separate the isomers of C5, C6, and C7 alkane to yield three different fractions: linear, monobranched, and di-branched. And the di-branched isomers are the preferred components to be separated and incorporated into the gasoline pool. And the question is, how do we separate the di-branched isomers from the monobranched isomers, and how do we separate the monobranched isomers from the linear isomers? And if we look at the boiling points of C6 and C7, we note that the differences are quite small. It's possible perhaps to separate the linear from the branched ones, but the separation of the di-branched isomers from the linear isomers is a difficult task. And that is the topic for discussion in my presentation today. I show here a process flow scheme for the alkane isomerization process, in which a feed mixture consisting of C5, C6, and C7 alkanes is fed to the isomerization reactor that is catalyzed by Mortonite catalyst. The products emerging from the isomerization reactor is a thermodynamic equilibrium of the isomers of C5 alkanes, C6 alkanes, and C7 alkanes. In the separation step, LTA5A zeolite is used in order to separate the linear isomers NC5, NC6, and NC7 that can pass through the narrow windows, typically of diameter 4 angstrom, 5 angstrom, and the bulkier monobranched and di-branched isomers are unable to hop from one cage to the adjacent cage, and they are recovered in the raffinate phase. The linear isomers can be recycled back to the alkane isomerization reactor. For background on the process details, I refer you to my 2 papers listed here. An improved process flow scheme would be to use MFI zeolite as an adsorbent in the separation unit. And the advantage of using the MFI adsorbent is that we can separate the di-branched isomers from the linear isomers and monobranched isomers, and the linear and monobranched isomers can be recycled back to the isomerization reactor, whereas the di-branched isomers that have significantly higher research octane numbers can be directed and incorporated into the gasoline pool. I refer you to my publication in Physical Chemistry and Chemical Physics, published in 2015. Also, see my presentation on entropic separations on my YouTube channel. I focus now on the separation with MFI adsorbent. MFI zeolite is a suitable adsorbent for separating alkane isomers. MFI stands for mobile 5. It has a set of intersecting channels of 5.5 angstrom. These are the straight channels, and in this direction we have the zigzag channels. These channels intersect at these locations, and there are 4 intersection sites per unit cell. The branched isomers of alkanes, say 2-methylbutane, 2-methylpentane, and 2,2-dimethylbutane, all the branched isomers prefer to locate at the intersection sites where it has more leg room. This is shown by the computational snapshots here. There are 4 intersection sites per unit cell, and the saturation capacities of the unary isotherms for these 3 isomers are all 4 molecules per unit cell. For 2-methylbutane, the Langmuir constant is 4.12 times 10 to the minus 5 Pascal minus 1. The corresponding Langmuir constant for 2,2-dimethylbutane is higher. It's 7.12 times 10 minus 5. And the Langmuir constant for 2-methylpentane is even higher than that of 2-methylbutane because of improved van der Waals interactions with the channel walls, and the Langmuir constant is 1.27 times 10 minus 4 Pascal minus 1. However, the diffusional time constants are shown here. These were determined experimentally, and these diffusional time constants are the highest for 2-methylbutane. This lowered slightly for 2-methylpentane, and the lowest diffusional time constant is for 2,2-dimethylbutane. Therefore, within the intersecting channels of MFI zeolite, 2-methylpentane has the highest adsorption strengths, but the di-branched 2,2-dimethylbutane has the lowest diffusivity. Let's examine how adsorption strengths and guest mobility play out against each other. And I demonstrate this by examining a set of 6 experiments reported by Joly-Maitre in the AICHE journal paper published in 2002. The analysis I will be presenting is based on my own paper published in ACS Omega in 2019. In these 6 figures, A, B, C, D, E, F, I plot the experimental data of Joly-Metre as published in the AICHE journal in 2002. The experimental data are shown by the symbols. These 2 experiments here are for binary mixtures of 2-methyl pentane and 2,2-dimethyl butane. The experiments show that the component to elute first is 2,2-dimethyl butane that has the lower adsorption strength and also the lower intracrystalline diffusivity as compared to 2-methyl pentane that has a higher adsorption strength and also a higher diffusion coefficient. The continuous solid lines are the breakthrough simulations ignoring diffusional influences, and we note that the match is poor because diffusional influences are strong. Diffusional influences make 2,2-dimethyl butane elute the adsorber earlier than anticipated by a model that ignores intracrystalline diffusional influences. Indeed, diffusional influences are helpful in the separations because there is a wider gap between the breakthrough times from experiments than those anticipated by a model that ignores diffusional influences. Put another way, adsorption and diffusion act synergistically in runs 17 and 18. The partial pressures indicated here are the partial pressures of the feed mixture at the inlet to the fixed bed adsorber packed with MFI pellets. The experiments shown here, these 4 set experiments run 19, 20, 21 and 22 for ternary mixtures of 2-methyl butane, 2-methyl pentane and 2,2-dimethyl butane. In all 4 experiments, the component to elute first is 2,2-dimethyl butane that has the lowest mobility within the intersecting channels of MFI zeolite. The component to elute last in all 4 experiments is 2-methyl pentane that has the highest adsorption strengths of the 3 components. What is interesting to note is that the simulations in which diffusional influences are considered to be of negligible importance, the component to elute first is 2-methyl butane, but this is not in agreement with the experiments because in the experiments 2,2-dimethyl butane elutes first. This reversal in the order of breakthroughs of 2-methyl butane and 2,2-dimethyl butane is purely ascribable to the significant differences in intracrystalline diffusion due to the significantly lower mobility of 2,2-dimethyl butane within MFI zeolite, 2,2-DMB elutes first. So diffusion overrides the hierarchy of adsorption. And this is also helpful in the separations because we want to recover 2,2-dimethylbutane for incorporation into the gasoline pool, and due to diffusional influences, the component to elute first and recovered in the raffinate phase is 2,2-dimethylbutane. So diffusional influences help separations. Let us demonstrate that quantitatively in the next slide. To model the breakthrough experiments published by Joly-Maitre, we need to take proper account of both adsorption and diffusion. And for modeling of diffusion inside the micropores, there is a need to incorporate the Maxwell-Stefan diffusion formulation, in which due account is taken of thermodynamic coupling effects. And I explained this in my 2019 paper published in ACS Omega. Watch also my YouTube presentation, Diffusion and Micropores. And there are other presentations on diffusional effects in zeolites and morphs that can be viewed on my YouTube channel. The set of 6 experiments can be reproduced nearly quantitatively by a model in which due account is taken of the interplay between adsorption and diffusion using the Maxwell-Stefan diffusional formulation, and the predictions of the breakthroughs are shown here by the continuous black lines. For all 6 experiments, there is one-to-one correspondence between experiments and simulations. So I conclude by saying that MFI zeolite is suitable for use in separation of alkane isomers. The separations are synergistic in nature because the diffusional influences serve to enhance the separations that is dictated by mixture adsorption equilibrium. And in my reckoning, MFI zeolite is the most suitable adsorbent for alkane isomer separations.